Okay, so in today's lecture, we will continue our discussion of conjugated dienes. We defined them and talked a little bit about their structure in our last lecture. And then we're going to talk about two reactions of conjugated dienes. The first one is the addition of HX. We've covered the addition of HX to alkenes, but when we're adding HX to a diene, the outcome can be different than when we're adding it just to a regular alkene. And then we will start talking about the Diels-Alder reaction, which is a very interesting reaction that occurs with dienes. So I've drawn here on the board the structure of 1,3-butadiene, our simplest conjugated diene. And I've drawn the bond lengths in. And the bond length of the carbon-carbon double bond in 1,3-butadiene, 1.34 angstroms, is exactly the same as the carbon-carbon double bond length in ethylene. So it's a normal carbon-carbon double bond length. However, the sigma bond that connects C2 and C3 in 1,3-butadiene is a little bit shorter than the carbon-carbon sigma bond in ethane. Okay, not a huge difference, but a measurable difference. And there are two reasons why this sigma bond is a little bit shorter than the sigma bond in ethane. The first one is due to greater S character. So this sigma bond between C2 and C3 and 1,3-butadiene is between two carbons that are sp2 hybridized. Okay, it's a sigma bond connecting sp2 carbons. So we have sp2 hybrid orbitals that are being used to make that sigma bond. And we know that hybrid orbitals with higher percent S character are held closer to the nucleus. And because of that, the bonds that they form are a little bit shorter because the electrons in those bonds are a little more strongly attracted to the nuclei that are involved. So that greater S character of those sp2 carbons relative to the sp3 carbons in ethane or other alkanes makes this sigma bond a little bit shorter. And then there's another reason, and that is due to the delocalization of the pi electrons. So we told you in our last lecture that when we have a conjugated diene, the 4 pi electrons are delocalized across the 4 carbons. We showed you an electrostatic potential map. And so that delocalization increases the electron density between carbon 2 and carbon 3. And that increased electron density leads to a higher bond order and therefore a shorter bond. And we can see that with resonance. I showed you the resonance structures. I'll show them to you again. So here's our major contributor of 1,3-butadiene. And we can draw a minor contributor where we have a double bond between C2 and C3 and a carbocation at one end and a carbanion at the other end. And then we have the other minor contributor that is identical, or equivalent, I should say, that we'll show with these dashed arrows, that has the position of the carbocation and the carbanion inverted. So these are definitely minor contributors, but they still do contribute. So in 1,3-butadiene, there's a small amount of double bond character for that bond between C2 and C3, and that's reflected in the slightly shorter bond length that we see. Okay, so those two reasons, the greater percent S character of those carbons involved in the sigma bond, as well as the delocalization of the pi electrons, which we see by these resonance structures, contributes to that shorter bond length. I mentioned in the last lecture that conjugation or delocalization of the electrons due to conjugation leads to stability, increased stability. So conjugated dienes are more stable than isolated dienes. And we learned last semester that heats of hydrogenation can be used as a way of comparing the relative stabilities of alkenes. So we're able to use heats of hydrogenation to determine the difference in energy, the difference in stability between a conjugated diene and an isolated diene. So we have this figure here up on the screen that shows us the difference in energy between 1,4-pentadiene, an isolated diene, and 1,3-pentadiene, or a conjugated diene. And so anyone would predict that, hopefully I should say, any student who's had Chem 351 should predict that the conjugated diene will be more stable or lower in energy than the isolated diene. But there's two reasons for that. One is conjugation, what we've just talked about. The other is the fact that our conjugated diene in this case has a disubstituted double bond, which is going to be more stable than the monosubstituted double bonds. 1,4-pentadiene has two monosubstituted double bonds, whereas 1,3-pentadiene has a monosubstituted and a disubstituted double bond. So how much of the difference in energy between these two alkenes is due to conjugation, and how much is due to the difference in substitution, the monosubstituted versus the disubstituted double bond? This figure here tells us that. It divides it up. So what we have on the left, 252 kilojoules per mole. You divide that by 4 and you get the value in kcals per mole, roughly 60. That is the heat of hydrogenation of our isolated diene, 1,4-pentadiene. And then right here, 126 kilojoules per mole, or exactly half of this value, is the heat of hydrogenation of 1-pentene. Okay? So what we see is that the heat of hydrogenation of 1,4-pentadiene is exactly twice that of 1-pentene. We would expect that because these two double bonds are just monosubstituted, and there's no difference in their heats of hydrogenation. Now we go over here on the right. As we would expect, we see a lower heat of hydrogenation for 1,3-pentadiene. We see that it is 26 kilojoules per mole. That would account to a little more than 6 kilocalories per mole of difference. But how much of that is coming from the conjugation and how much from the trans disubstituted versus monosubstituted alkene? What we're doing over here is we're subtracting the heat of hydrogenation for E, or trans 2-pentene. That's 115 kilojoules per mole. It's less than the heat of hydrogenation of 1-pentene, as we would expect, okay? This value is not twice that value, okay? So if you subtract 115 from 226, you get 111. And so that would be the heat of hydrogenation of a conjugated monosubstituted alkene versus 126 kilojoules per mole, which is the heat of hydrogenation for an isolated or non-conjugated terminal alkene. So if we subtract this number from that number, we get a value for the amount of stabilization that we gain from having conjugated dienes versus isolated dienes. And so if we do that math, 126 minus 115, minus 111 gives us 15 kilojoules per mole. And that comes out to about 3.6 kilocalories per mole. And we refer to this value as resonance energy. Okay? Resonance energy is an important term to know. It is the stability due to resonance. So in the case of a 1,3-diene, we can say that that molecule gains 3.6 kcals per mole of stability, or in other words, is 3.6 kcals per mole in energy, lower in energy than an isolated diene. Okay, so fortunately, because of heats of hydrogenation, we're actually able to measure the stability that is available due to conjugation And we find that in a conjugated diene system, that value is 3.6 kcals per mole. When we get to our next chapter, chapter 17, and we're talking about cyclic conjugated systems, we'll find that they have much higher amounts of resonance energy, but we can also measure it in that case. So resonance energy is a concept that we're going to explore not only in this chapter, but in our next chapter as well. Okay, so now that we understand the increased stability and we've been able to measure the increased stability of a conjugated diene relative to an isolated diene, we're now going to discuss specific reactions that either are only possible with conjugated dienes or will give a different outcome with a conjugated diene when compared to an isolated diene. And the first reaction is one we've seen before, the addition of HX. So if we take an isolated diene, our 1,4-pentadiene that we were looking at on the screen, and we react that with HBr, and we make sure that we're careful and we only use one equivalent of our HBr, then we're going to get the Markovnikov product here, right, where the bromine attaches to the less substituted carbon. We form the more stable carbocation. It is going to be a chiral molecule. I'm going to go ahead and draw a squiggly line here, a squiggly bond. That's kind of a shorthand way of indicating a racemic mixture, where that bromine is going to be both coming out of the screen or the board and going back into the board. If we perform the same reaction with a conjugated diene, the outcome is different. We obtain two different constitutional isomers, and the major product differs depending on the temperature of the reaction. Okay, so if we use one equivalent of HBr with a 1,3-diene, we can obtain, and I'm going to draw this squiggly line again, indicating that this is a racemic molecule. We can obtain a product very similar to the one that I showed you above, and this is referred to as the 1,2 addition product, because we've added the proton and the bromine atom to carbons that are adjacent to each other. But the other product that is obtained has the proton and the bromine on the ends of the molecule. And so this is known as the 1,4 addition product. Okay? So why do we get two different products? Well, it has to do with the mechanism of the reaction. We'll go ahead and raise this up. I don't think we have enough room to write that mechanism on what remains of the board there. So we start out by protonating our alkene. So the pi electrons attack the proton, and we're going to get the more substituted carbocation. Okay. And in this case, this is an allylic carbocation. This is a conjugated system, as we learned in our last lecture, and it is a resonance stabilized system. So we have two different resonance structures of this allylic carbocation. Okay. So because we have this resonance stabilized carbocation, we know we only have one carbocation that has partial positive charges on this carbon and that carbon. So if the bromide attacks this carbon, then we obtain the 1,2 addition product as a racemic mixture. Okay? But if the bromide attacks the carbon at the end of the chain, then we obtain the 1,4 addition product. Okay? So that's how we obtain the two different products in this reaction. The bromide will attack, and let me put the negative charge on that bromide. The bromide will attack either of these two carbons that share the positive charge in this conjugated delocalized carbocation. So as I alluded to, the interesting thing is the major product of this reaction differs depending on the temperature at which the reaction is conducted. So if we conduct this reaction at a very low temperature, minus 80 degrees, if you have a bath where you put dry ice and acetone, you can get down very close to minus 80 degrees. That's basically the temperature that the Pfizer vaccine has to be stored at. If you're running this reaction at that temperature, you get a 4-to-1 mixture favoring the 1,2 addition product, okay? And we're going to refer to the 1,2 addition product as the kinetic product, okay? That means it's the product that is formed the fastest or formed the most rapidly, okay? The 1,2 addition product is formed the fastest, and at minus 80 degrees, it predominates. It is the major product, okay? However, if we warm the reaction mixture up above room temperature, 40 degrees Celsius is above room temperature, this ratio inverts. We end up with a 1-to-4 ratio. And the 1,4 addition product is the major product. If you've looked at the structures of these two products, you may have recognized that the 1,4 addition product is more stable. It's lower in energy because it has a disubstituted alkene as opposed to a monosubstituted alkene. So we refer to the 1,4 addition product as the thermodynamic product because it is the more stable product, okay? Up until now, in the reactions we've studied, the major product of the reaction has been the thermodynamic product. So the kinetic product and the thermodynamic product have been the same. But I warned you earlier in class, because kinetics and thermodynamics are not connected, they're independent of each other. I warned you that we would come to a day where the product that's formed the fastest is not the major product of the reaction. And this is that day. At low temperature, the kinetic product, which is less stable than the thermodynamic product, is the major product. The only way we can have the less stable product be the major product is if it is formed faster. So the data here tells us that this product, our kinetic product, must be the one that is formed faster in the reaction. Even at minus 40, this product is formed faster, and I'll explain why in a moment. But the reason that we can obtain the thermodynamic product as the major product is at the higher temperature, we have an equilibrium. We're able to reverse the formation of the kinetic product and generate the thermodynamic product. How does that happen? Well, we know that with the energy available from heat, we're able to cleave carbon-bromine bonds and generate carbocations. That happens in SN1 reactions. That happens in E1 reactions. Okay, so we are losing bromide in this step. We generate this carbocation. Of course, this is a resonance stabilized carbocation. And then the bromide that is released can come back in and attack either at this carbon or that carbon. If it attacks here, we simply go back to the starting material. But if it attacks over here, we are able to proceed on to the 1,4 product, okay? And so when we set up this equilibrium, of course, this is reversible. The bromine can still pop off. But if we set up this equilibrium, we're going to end up with the more stable product as the major product. And so the thermodynamic product will predominate. At minus 80 degrees, we don't have enough energy to reverse the reaction. We don't have enough energy to break that carbon-bromine bond. So at minus 80 degrees, the product that's formed the fastest is the major product. It has no ability to equilibrate to generate the thermodynamic product. But at a temperature higher than room temperature, we now have enough energy available to break that bond, generate this resonance stabilized, or regenerate the resonance stabilized carbocation, and then attack at the terminal carbon to generate the more stable product. Okay? So, why is the less stable product formed faster? Let's take a look at an energy diagram. This shows us in general how this can happen. So we have one species A, which is our allylic carbocation intermediate, that can react in two ways to generate two different products. We see here from this energy diagram that B is higher in energy than C. However, we know that energy of activation is directly proportional, or inversely proportional, I should say, to reaction rate. So the pathway leading to our higher energy product has a lower energy transition state, and therefore a lower energy of activation and a faster reaction. So the lower energy transition state leads to the higher energy product. The higher energy transition state leads to the lower energy product. Okay, so that's in general how this happens. But specifically, why is the transition state leading to the higher energy product lower in energy? Let's take a look at the next diagram here, and that will help us understand this. Okay? So the addition of HX, or HBr in this case, to a 1,3-diene has two steps. First step, we protonate, generate our allylic carbocation. Second step, the bromide comes in and attacks and gives us the product. It is the second step that determines which product is formed. We know the first step is the slow step, or the rate determining step, but the second step is the product determining step in this case. Okay? So we only have one pathway leading from the 1,3-diene to our resonance stabilized allylic carbocation, and you see we've drawn the hybrid structure for you here in this case. And then two pathways that lead from that intermediate to the products. Okay? Now, I wish that when they drew this figure, they had drawn the bromide adjacent to this carbon instead of over here. Because what happens when you protonate this alkene, your bromide was still associated with your proton right up until the alkene was protonated. So right after you protonate, when you get to the carbocation, the bromide is going to be in close proximity to this carbon and further away from that carbon. Okay? So if you were to ask, what is the lowest energy pathway to get from this intermediate to a product? It's going to be the bromide attacking the positively charged carbon that it is closest to in space. Okay? The bromide can certainly attack the carbon on the end, but it has to travel through space to get there, and that requires energy. And so that energy that's required for the bromide to travel to the terminus of this diene is reflected in that higher energy of activation. So this is what is known as a proximity effect. When you protonate the C1, the carbon on the end of the chain, the bromide is closest to C2. Okay? And so it costs less energy for the bromide to attack that carbon, and that's reflected in the lower energy of the blue transition state. It requires energy for the bromide to travel to the other end of the chain, and that's reflected in the higher energy of that transition state. So this is why the less stable product, the 1,2 product, is formed faster due to this proximity effect. It's important to note that that product is formed faster regardless of the temperature at which you run the reaction. When we run the reaction at 40 degrees, in the beginning seconds or maybe even minutes of the reaction, the 1,2 product is the major product. But when you have a temperature that allows you to reverse the reaction, to break the carbon-bromine bond, then through equilibrium, you're able to obtain the more stable product as the major product. So as the reaction unfolds at 40 degrees, we start out with the kinetic product as the major product. But over time, we end up with the thermodynamic product as the major product. In contrast, at minus 80, the kinetic product is always the major product because we don't have enough energy available to break that carbon-bromine bond and reverse the second step of the addition of HX. Okay? So this is an important concept. I hope you spend some time with these two figures from the book because they do a great job of explaining the issue of a kinetic product versus a thermodynamic product, and how, in this case, the addition of HX to a 1,3-diene, the kinetic and thermodynamic products are not the same. Okay, now we're going to move on and talk about the Diels-Alder reaction. So this is a name reaction. It's named after two German chemists, Otto Diels and Kurt Alder. And this is a key reaction of dienes. So in a Diels-Alder reaction, you have a diene, such as 1,3-butadiene. And then you have a dienophile. A dienophile is an alkene. Right? Dienophile means lover of dienes. We should all be dienophiles because dienes are really cool and can do a lot of interesting things. But our dienophiles can have substituents on them. Of course, our dienes can as well, but we're not drawing them that way. And when you heat these up, heat is required for a Diels-Alder reaction. We're going to form a 6-membered ring. And it's going to be a really interesting mechanism because we're going to have 3 pairs of pi electrons moving to form that 6-membered ring. Okay? So we have pi electrons from the diene attacking our dienophile. Pi electrons from the dienophile attacking the other end of the diene. And then we have these pi electrons moving. So what we end up with is a cyclohexene, a 6-membered ring with a double bond. And then we have our substituents. We'll talk about this later on, the stereochemistry of the Diels-Alder reaction. It is a stereospecific reaction. The groups that are cis to each other in the dienophile will be cis to each other in the product. So you see the way that I've drawn it, A and X are cis in the product, cyclohexene. A and Y are trans in the dienophile. They're trans to each other in the cyclohexene product. So this is a stereospecific reaction where a specific isomer of our dienophile will lead to a specific isomer of our product. If we had A and Y cis to each other in the dienophile, they would have to be cis to each other in the product. Okay? So the Diels-Alder reaction is a cycloaddition. We mentioned cycloadditions in 351M. We talked about how certain steps in oxidation reactions, osmium tetroxide or ozone oxidation reactions, were cycloadditions. So these are additions that form rings. So this is an addition reaction. We can say the diene is adding to the dienophile. So it is an addition reaction. It is also something we refer to as a paracyclic reaction. Okay? So a paracyclic reaction is a concerted reaction. Right? A concerted reaction is a one-step reaction with a cyclic transition state. Okay? So the transition state for the Diels-Alder reaction looks like this. A lot of dashed lines because we have 3 bonds that are breaking and 3 bonds that are being formed. And so we end up with 6 dashed lines. There are other paracyclic reactions, but the Diels-Alder reaction is the most famous and probably the most useful of those paracyclic reactions. So heat is required because we have to have a high degree of organization in this transition state. We have to have the diene and the dienophile come together in just the right orientation in order for the orbitals to overlap for those 6 pairs of electrons to reorganize themselves. If we analyze this reaction in terms of bonds that are formed and bonds that are broken, you see that we're breaking 3 pi bonds in this reaction. And in their place, we're forming 2 sigma bonds. These dotted lines are the sigma bonds that are forming. These are the partially formed bonds at the transition state. These sigma bonds right here are the ones that are formed in the product. And then we're also forming 1 pi bond. This pi bond right here, represented by this dashed line in the transition state, is formed. So the Diels-Alder reaction is thermodynamically favored. It's exothermic because we're breaking 3 pi bonds and we're forming 2 stronger sigma bonds and then 1 pi bond, which is roughly equivalent in strength to the pi bonds that are broken. So a little bit of interesting history behind the Diels-Alder reaction. Otto Diels and Kurt Alder in 1928 reported the first example of the Diels-Alder reaction. So they took 1,3-butadiene and they reacted it with this dienophile. I didn't give myself enough room to draw the dienophile. So let me write the 1928 over here. Okay. So they reacted these 2 species together and they heated it up. We draw our 3 curved arrows and they ended up with this product. And we know that these groups have to be cis to each other in the product because they're cis to each other in the dienophile starting material. So the product looked like this. You'll notice this is a meso compound. It has a plane of symmetry, but these 2, so it's achiral, but these 2 hydrogens are cis to each other. Okay. Now, it turns out that other German chemists had very likely performed Diels-Alder reactions previous to 1928, but none of them had correctly identified the products that they formed. So Diels and Alder were the first chemists to both perform a Diels-Alder reaction and correctly identify the product. So that's why they got the reaction named after them. Interestingly enough, in the first paper they published on this, they had a statement I've never seen anybody else put in a scientific paper, which is, they said, we reserve for ourselves the rights to further explore this reaction. They were basically telling other organic chemists to back off and not touch their reaction. This is quite arrogant, and fortunately, it was not followed. There were many other chemists who jumped in and investigated the Diels-Alder reaction. If you search for the Diels-Alder reaction in SciFinder, the best scientific database for searching the chemical literature, you'll find over 38,000 papers on the Diels-Alder reaction. So a hugely important topic. So they did not get their wish of having the reaction reserved for them. However, as consolation prizes, they did get the reaction named after themselves. And in 1950, they shared the Nobel Prize for discovering this reaction. So hopefully that was a good enough consolation prize for them. Okay? So let's talk a little bit about rules governing Diels-Alder reactions. Go ahead and erase the board and talk about some rules that are important for Diels-Alder reactions. So the first rule is that the diene can only react if it is in the S-cis conformation. Sorry, I broke the chalk. Okay. So we learned the difference between S-trans and S-cis in our last lecture. So this would be an S-trans conformation, and the diene cannot react in a Diels-Alder reaction if it is S-trans. But an acyclic diene is able to rotate. There would be an equilibrium here between these two conformations, but it's able to rotate about the carbon-carbon sigma bond and rotate into the other planar conjugated conformation, the S-cis conformation. Knowing that the Diels-Alder reaction is a concerted process, that there's no intermediate, that all the bonds are being formed and broken at the same time, we can understand why the diene must be in the S-cis conformation. We need to have the two terminal carbons of our diene pointing towards the dienophile in order to have that concerted process. If we have one pointing towards and one pointing away, we cannot have a concerted one-step paracyclic reaction. Okay, so that's why we have to have the S-cis conformation. We said last time this conformation is higher in energy than the trans because of the steric strain, but it is accessible at room temperature and at the elevated temperatures of the reaction, so it's not a problem for acyclic dienes. Acyclic dienes can always form the S-cis conformation. However, with cyclic dienes, because we do not have free rotation in cyclic dienes, some will react in Diels-Alder reactions and some are unreactive. Okay? So here we have cyclopentadiene. Cyclopentadiene is a very good diene in Diels-Alder reactions. It's locked into the S-cis conformation. Okay? So cyclopentadiene will be reactive in a Diels-Alder reaction. However, this particular diene, this methylene cyclohexene species, this would be 3-methylene cyclohexene, you see that it's impossible for this diene to get in the S-cis conformation. So this diene here, this methylene cyclohexene, is unreactive. It will not participate in a Diels-Alder reaction. So this rule has a consequence, and the consequence is that some of our cyclic dienes will not participate in Diels-Alder reactions. Okay? All right. Our next rule that we will discuss is that electron withdrawing groups on the dienophile increase the reaction rate. Okay? And those electron withdrawing groups in most cases are carbonyl groups. I erased it, but if you looked at the original, if you go back in the video and look at the original reaction that Diels and Alder conducted, there were carbonyl groups that were conjugated to the double bond of the dienophile. If we look on this, I'll go back to that one in a moment. If we look on the screen here, you see that these are some common dienophiles. And you see that they all have carbonyl groups. This aldehyde has a carbonyl group, even though it's not drawn out. But you see all of these have carbonyl groups that are conjugated to double bonds. So how are those carbonyl groups electron withdrawing groups? Well, we can draw one of them, methylvinyl ketone. And we know that this carbonyl group is polarized. So we have a partial negative charge on that oxygen, a partial positive charge on the carbon. And so that carbon with the partial positive charge will inductively withdraw electrons from the pi electrons of that alkene. Okay, and then we can use resonance to show the electron withdrawing effect of a carbonyl. In our last lecture, we talked about the minor contributor that we have when we have a double bond between two atoms of differing electronegativities. And then this minor contributor leads to the presence of a second minor contributor that shows us withdrawing electrons from the alkene of our dienophile. Okay, so either by resonance or by induction, we can see that carbonyl groups conjugated to alkenes are going to withdraw electrons from those alkenes. And we see all of these dienophiles up on the screen that are that have carbonyls conjugated to alkenes. These are fast-reacting dienophiles where we have an increased reaction rate. So why do electron withdrawing groups conjugated to dienophiles, to the alkenes of dienophiles, increase the reaction rate? To understand this, we actually have to use molecular orbital theory. You know that we talked about molecular orbital theory back in chapter 1, and I told you we weren't going to use it much, if at all, in 351M, but that we would use it when we got to 352M. Well, now is the time. Lecture 2 of 352M, we're now going to use molecular orbital theory to explain why electron withdrawing groups attached to dienophiles increase the reaction rate. We're not going to complete the explanation in today's lecture, but we're going to start it, and then we're going to finish it in the next lecture. So we have to consider the frontier molecular orbitals, okay? And I'll explain what we mean by frontier molecular orbitals in a minute. Frontier molecular orbitals, or MOs. MOs is our abbreviation that we typically use for molecular orbitals. So we have molecular orbitals that are occupied. Those are lower in energy. Molecular orbitals that are unoccupied, those are higher in energy, okay? And so the highest energy occupied molecular orbital is going to be on the frontier between the occupied and the unoccupied. And that's referred to as the HOMO. That stands for highest occupied molecular orbital. Okay? And then our other frontier molecular orbital is going to be the lowest energy unoccupied molecular orbital, or the LUMO. So LUMO stands for lowest unoccupied molecular orbital. Okay? So in a reaction, generally speaking, the highest occupied molecular orbital of the nucleophile is going to contain the most nucleophilic electrons in that molecule, right? If those electrons are in the highest energy occupied orbital, they're going to be the most reactive. Those are going to be the electrons participating in a reaction, okay? And on an electrophile, it's going to be an unoccupied orbital that's getting attacked by electrons from the nucleophile. And it's going to be the lowest energy unoccupied molecular orbital of that electrophile that is getting attacked. So this is a general principle that applies to many reactions, not just the Diels-Alder reaction. But this is the first reaction that we're analyzing in terms of molecular orbitals. Okay? So let's look at a simple Diels-Alder reaction between the simplest one possible, with ethylene as our dienophile and 1,3-butadiene as our diene. Okay? So to look at the frontier molecular orbitals of a diene and a dienophile, we only need to look at what we will call the pi molecular orbitals. Okay? Pi bonds are weaker, higher in energy than sigma bonds. When we've seen reactions of alkenes, we've always involved the pi bonds. We haven't involved the sigma bonds in most cases. And so those pi molecular orbitals are going to be on the frontier. So the occupied pi molecular orbitals will be higher in energy than the occupied sigma molecular orbitals. Conversely, the unoccupied pi molecular orbitals, or the pi star molecular orbitals, will be lower in energy than the unoccupied sigma molecular orbitals. So these pi molecular orbitals are going to be on the frontier, and so they're the only ones we need to consider as we're thinking about molecular orbitals and the Diels-Alder reaction. Now remember, a key principle we learned in molecular orbitals is that the number of molecular orbitals in a molecule equals the number of atomic orbitals used to create those molecular orbitals. In ethylene, we have 2 p orbitals that overlap to create the pi system. So we have 2 atomic orbitals, and therefore we would end up with 2 pi molecular orbitals in ethylene. So another principle of molecular orbitals is that the lowest energy molecular orbital will always have no nodes, 0 nodes, meaning that the sign of the orbital does not change as you go from atom to atom. So what do we mean by that? Well, we need to draw it out to show you. So here's ethylene, the 2 carbons. Our p orbitals overlap to make molecular orbitals. If we have the upper lobes, both upper lobes shaded, this is what I mean by saying there are 0 nodes. The shading indicates the sign. Remember, a molecular orbital is simply a fancy mathematical equation. It has a sign. It's either positive or negative at different locations in space. And so this molecular orbital has 0 nodes. So that's our lowest molecular orbital, lowest energy molecular orbital in ethylene. So this is energy going up. And then above that, if we flip the sign of one of our lobes there, now we end up with a node. The node is often indicated by a dashed line. As we go from this carbon to that carbon, the sign of the molecular orbital is changing, so we have 1 node. So this molecular orbital is higher in energy than that molecular orbital, okay? So we have 2 pi electrons in ethylene. Those 2 pi electrons are both going to occupy the lower energy molecular orbital, and the higher energy molecular orbital will be empty. So this is our pi molecular orbital. This is our pi star or anti-bonding molecular orbital. The presence of a node between the 2 atoms is what indicates that this is an anti-bonding molecular orbital. If you put electrons in that, it would not contribute to bonding between these 2 atoms, whereas here it would because there is not a node, okay? So the highest occupied molecular orbital of ethylene is the one on the bottom. The lowest unoccupied molecular orbital of ethylene is the one on the top. And it is this one that is relevant to the Diels-Alder reaction because ethylene is the dienophile. It is the electrophile in the Diels-Alder reaction. And the diene is the nucleophile, okay? In our next lecture, we will talk about the molecular orbitals of 1,3-butadiene, and we'll show how the HOMO and the LUMO interact. Before we finish, there was one thing I skipped that we'll come back to. This figure here shows an example of a Diels-Alder reaction. Tetrodotoxin is this very interesting molecule here that has several 6-membered rings, several nitrogens and oxygens. This is a famous toxin. It is present in the Japanese pufferfish, or fugu. Fugu is the specialty that can kill you, that if you eat it, at least in Japan and hopefully in other countries, the chef has to be specially licensed to know how to prepare the fugu to either remove or eliminate sufficient amounts of the toxin so that you survive. This toxin gives you a zing on your tongue, so people like to eat it, but obviously they don't like to eat too much of it. Okay? So tetrodotoxin is a neurotoxin. It's involved in the nervous system, and chemists who wanted to study it learned how to synthesize it, and they used the Diels-Alder reaction. If you were in the room, I'd ask you to raise your hands if you'd ever eaten fugu before. I'll raise my hand because I have eaten fugu before. I wasn't taking my life into my own hands because I was eating a special farm-raised version of the Japanese pufferfish that was bred to produce lower amounts of the tetrodotoxin. I happened to be the guest of honor at a dinner in China. I was being hosted by a prominent scientist in China, and he was really excited. I don't know why he was excited that I was his guest, but for some reason he was. And so he threw this dinner and the main dish was this Japanese pufferfish. And so I had no choice but to try it because I was the guest of honor. I will tell you that I let the host eat it first before I tasted it. It was really good. It was delicious. I had that zing on my tongue that I mentioned to you, so I know it's real. And I'm still here standing. I didn't have any ill effects. And so because I was eating farm-raised pufferfish instead of pufferfish in the wild, they had been bred to produce smaller amounts of the tetrodotoxin. So tetrodotoxin is a very interesting molecule. It's a neurotoxin. And because it has so many six-membered rings, you can see that the six-membered ring shown here is the one that is prepared by the Diels-Alder reaction. All right, so we'll finish there for today. We'll continue our discussion of the Diels-Alder reaction in our next lecture, as well as talking about some other issues of conjugation, and then we will start chapter 17, just the first two sections of chapter 17 in our next lecture.